overcoming IMFs, things like that. So the pieces that we relate to, school remote, guys. Batteries don't want to work. Okay. So the things that are related to what you should know in terms of multiple choice, these terms we utilize in the solutions, like properties of solutions. So that first gamut of little, like 12 questions that were related to that, I would know some of those and how we approach them. I think I printed out this first bit of notes, so you can definitely go back and look at the printed slides or through the textbook. Your little MSI reading has maybe a couple paragraphs on it. What's the difference between hydrated and ionized? Ionized means forms ions in solution. Well, it's the only thing that's going to form ions in solutions. Ionic compounds, and what else can break into ions? Acids, right? Strong acids. That would be considered a strong electrolyte. Hydrated compounds would be things that are light wet. Say again? So anything covalent is just simply surrounded by water. It's like water's ganging up on it. It does not break it apart, though. It does not ionize. It does not dissociate. What you could say is it gets particulated. It's just sugar, 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 sugar versus a clump of sugar. Okay, and I think the other ones are actually kind of self-explanatory if you think about what the process is. I want to talk about this one in a second with an example. Premise of distillation and chromatography, there were two, it said lab questions, 2 questions. Which one do you guys think I'm going to ask about? Oh, okay, those 2. All right, so you should know the premise of those, like what property they focus on to allow for separation. Positive and negative deviation from Raoult's law. You guys talk about that first, and maybe give some examples of what will cause positive or negative deviation. Go back in your nose. Raoult's law is the one with vapor pressure. It's one of the favorite properties. All right, Gigi, can you give me the definition of the phrasing we could use for the difference between positive and negative deviation using the vapor pressure law, Raoult's law? So the IMFs of solvent and solute are weak. Okay, so what does that do to the vapor pressure of this combined solution? Well, I won't say, I could say solvent and solute, but really, it's like we're talking 2 liquids together, so we both call them technically solvents, but we do have to identify there's a difference. So liquid 1 and liquid 2, okay? And if the IMFs are weak, what does that do to the vapor pressure? Say again? It just increases, right? So pH solution of A plus B, we'll just call those A and B, is higher than we would anticipate. What kind of compounds would do that? Give me just one example. Compound A, compound B. What things would not interact? Oil's not very volatile. It's got to be volatile, guys. If not, it's not going to have any vapor pressure. Water is technically volatile, so I can do that. Acids interact with water pretty well. They're polar most of the time. Acetone's polar, water's polar. Ethanol's polar, water's polar. Hexanes, yeah, things like nonpolar substances. So hexane and water, not going to interact, right? 2 totally different compound types, nonpolar and polar. They don't interact very well. So not only is water going to be its own volatile self, and hexane will as well, but combined, they don't want to be near each other, so it kind of even gives them extra push to be more volatile. So negative deviation, everybody, IMFs are strong. So we have a volatile substance A, volatile substance B. They're both vaporizing, but when we put them together, what happens to pH solution? It goes down. So pH solution of A and B is technically lower in vapor pressure than we thought they would be when they just combine naturally. What kind of substances would do that? Give me an example. You had some great examples earlier. Water and acetone. Okay, so acetone has a ketone group, which is the C double bond O, so it's got a dipole. It's got the ability to form a dipole-dipole interaction. What else? Ethanol. Anything else? Those are good examples. Okay, polar compound. Okay, so technically, we all know like acetone's like nail polish remover, so it kind of smells really bad. If you mix it with water, it actually tones down the vaporization, so then you don't smell it as much. So like 100% acetone is going to be very volatile, whereas like 20% acetone is going to be not so volatile. And then ethanol, same thing. All right, and then lastly, IMFs and the cumulative structure, or how cumulative effects of IMFs can distort properties. So normally we say, what's the order of increasing strength of IMF? LDF, dipole-dipole, hydrogen bonding, ion dipole. That is the trend, right? That's assuming we are comparing one molecule that's very similar in size, structure, molecular weight, polarizability. So it's like a very, very similar comparison. But if you're comparing like huge molecules to one, like HCl, that's going to really distort how we think about IMF. So this was the part on your lab. I didn't get to review the lab with you afterwards. The IMF lab, we saw like there was a deviation from what we expected the evaporation or the boiling point trend to look like versus what we saw in the lab. A couple of you guys were spot on. Can anybody help me out here? So like we had butanol. Know that these are H's, and versus what was higher than butanol was one of the highest ones, right? You guys know what lab I'm talking about. What was next in that lab? Okay, but that makes sense. They're all relatively high. Was there a nonpolar one?
There was like you had like some sort of really big something that was like higher.
Which one? Okay, so I'm going to just make up some data real fast. So let's just pretend acetone okay, so CH3, C double bond O. Let's just say acetone was higher in boiling point and this one was. So relatively, they're not that different in their molecular weight because we have some similar structure stuff going on here. But we have a polar molecule and a polar molecule, but what IMFs will go into play with the acetone? Okay, so this will be dipole because it's just got the polar group here, but it's not a hydrogen bonded ability group. And then we have this one, which is what? It's got an alcohol group. Do alcohols dissociate? Yay or nay? No, right? So do not dissociate alcohols. Important for your test. Alcohols do not, they're covalent structures, they're not going to dissociate. But this one has the ability to hydrogen bond with other butanols or water or whatever else. Okay, so theoretically, the hydrogen bond should win, right? It should be the highest. But in this case, let's say our data suggested the acetone one, the dipole-dipole one. So then you have to consider what are some other structural pieces of this that would play into this. So this is not exactly correct according to our lab, but what you'd have to consider is how close can these methyl groups get to other methyl groups versus how close can this carbon chain get to other carbon chains. Now theoretically a straight chain alkane, straight chain carbons, right, can stack, which makes them very, very strong in their LDFs. And this like kind of branch structure doesn't stack very well, so it's weaker in its IMFs. So basically if things can get closer, they're going to do a great job attracting. They're going to have a higher physical property, whichever one we're talking about. If things are branched and kind of chunky, they don't get very close. They have lower IMFs. They have lower physical properties. So you have to be able to speak to that from the words branch structure, straight chain alkane or straight chain carbon chain, or talk about the surface-to-surface contact, just so we're able to kind of morph our explanations to meet the data. The data says something, we have to explain it the way the data says. So I'm going to give you a better example of this in just a second. Is there anything else? Yeah. Don't say break. Okay. Talk in your groups first. What you guys can think of before I elaborate. All right, give me some keywords. Chase's table, give me a keyword here, or key phrase. Key thought.
Methanol is more polar than
More polar. They both have an all, right? So they both have an alcohol group. How is it more polar?
well, we just saw the curves like so water's polar.
Okay, so we're trying to morph our explanation to meet the data, because the data says methanol is more polar or more soluble in water. It does not say it's more polar though, so that we're morphing wrong here. It's close because you're trying to suggest it's more light, but really we're going to talk about pentanol and how it's less light. Does that make sense? That direction we're going to take? Just because it's saying methanol is more like water than pentanol is not necessarily correct. But saying that pentanol is less like water, we could probably get away with, but we would never say that. We have to explain it. Megan's table. What you guys got? Okay, that's a true statement. Methanol is smaller than pentanol, but it's not does not include the fact that methanol is more polarizable. Is that what you guys are suggesting? Okay, so not quite. Can I get another table? What about the carbon chain? So it has a larger what region? Non-polar region. Okay. So in this case, we're talking about solubility, right? The case we were just speaking of earlier with acetone and ethanol or phenol, that was boiling point. When we talk about melting points and boiling points and freezing points, anything that's like compound A to compound A, talking about their interactions, you can do it. You can do LDF, you can talk about polarizability, you can talk about hydrogen bonding, strength of attractions, yada, yada, yada. You can talk about surface-to-surface contacts and so forth. But when we're talking about mixing a compound with another compound, you have to think about, one, how can they interact, and why is this one not interacting well? That's your focus. Why is pentanol not interacting well? And it has to do with its nonpolar region, because we know water is polar. It's teeny tiny, it's polar. So this is methanol, right? How does water interact with methanol? Like, draw the structure for me. And then just draw how water would interact with it. Meaning IMF, meaning hydrogen bond. Because you have a drawing feature on your, I think it's on your response. Yeah, that's on your response. Alright, so are we on water interacting on the left or the right of the molecule? On the right, makes only OH group. Does that make sense? This is the polar region, this is the non-polar region. Water's not going to interact well over here at all. The teeniest, tiniest of LDFs, but nothing significant at all. So how are we drawing water? Like what's pointing where? So who's H and who's O? Okay, so the hydrogen from the water is close to the oxygen of methanol. I like it. Okay, so you could draw it like that. You could draw the water pointing its partial positive at the partial negative of methanol. You also could have drawn me, alternatively, you also could have drawn me the O close to the H part of the alcohol. So either one of those would work. And if it says on a structural drawing, like draw 2 or draw 1 or draw 4, follow those instructions, don't draw more or less. Okay, so what's going to happen is water's going to do this on 3 sides probably. It's going to do a really good job of submerging the methanol. This methyl group is kind of small, so it's just going to get kind of squished in between water molecules. Water's not necessarily tracking it, but it's able to pull it into solution quite well. Now, pentanol, how does it differ? Much, much larger carbon chain, right? So I'm going to draw 1, 2, 3, 4, 5. H, 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 H. Okay, so we have a really, really large nonpolar carbon chain, which is trying to get submerged in water. It's trying to get interacting, but we still only have this small portion over here that's interacting with water. What's happening over here? They're not interacting with water, so if you're not interacting with water, who is this carbon chain going to be interacting with? Other pentanols. So we've got pentanols stacking on pentanols, stacking on pentanols, stacking on pentanols. So they're clumping together because of their polarizable region, which makes their LDFs super, super, super strong. C times 5, C5, H11, OH, sorry. Yeah. So we've got these just stacking on each other like crazy. Water is trying to interact, but the hydrogen bond region is not strong, is not going to have strong enough interaction versus the nonpolar region, making pentanol insoluble in water. That's about it. But there is a break point on carbon chains, so I'm going to let you read before I just start yapping. Or you can see that. Just give me a thumbs up when you're done. So in the end, basically the larger nonpolar region, the larger the nonpolar region is, it makes it less soluble in water. Therefore, we would say it's insoluble or slightly soluble. In the smaller nonpolar region, like meth, F, and prop, is going to leave it to be more soluble in water, so therefore we just call it soluble. We don't differentiate between those. So the break point is usually around propanol. That's what we see a lot of solutions of, like isopropyl alcohol. You know, 75%, 95%, because it's really, it can be concentrated in a harmless fashion, but also it can be soluble in water. So I just wanted to reference the solubility differences, because that's one of the physical properties you should be very aware of, plus like normal ones like boiling point and freezing point. Okay? And I think, I'll review FRQs at the end of class. Okay? So can you guys grab a laptop? I'm going to show you guys what to do first. I had to grab it earlier, but didn't do it. Grab a laptop, please, and go to this bit.ly address when you get there. Alright, so I know you're into this bit.ly address, but I'll explain to you the premise, and it's pretty simple. I'm going to assign you to a group for a couple of different spectra types. Who's ever heard of UV spectroscopy? UV vis spectroscopy. Who's heard of UV vis? What do you think that's referencing? Ultraviolet and visible light, right? It's a part of the electromagnetic spectrum, but it's just a small portion of it. So it's got a very strict range of energy and frequency and wavelength. IR spectroscopy, what do you think that one's referencing? Infrared. So is that longer or shorter waves than UV? Longer. So greater or lesser energy? Lesser energy. Okay. And then who's ever heard of microwaves? Right. Where's that out on the spectrum? Is it high energy or low energy? Lower energy than like gamma, for example. Okay, so essentially, when you get to this link, I know you're not there yet, but I'll show you this now. Oops, dang it. Okay. So what you're going to do is you're going to get one of the groups of either the spectra, 1, 2, 3, or sorry, not microwave, mass spectra. Microwaves I'll talk about at the end. And then the other version of it is actually application of these spectra, which is going to be within labs. So this Royal Society of Chemists, it's there in England, they did a really good job of publishing some basic information on this, and I don't expect us to be experts. I expect us to have some talking knowledge and some working knowledge of the content, but not so far that you're confused. I want you to get the basics, okay? So the basics are the things, these things that I'm asking for. What is your type of spectrum? So like, what is it? Give us a little bit of really what it is. 2, why do we need it? So like, why is it important in chemistry? Why do we need UV vis? Why do we need IR? Why do we need mass? And then how do we utilize it in the real world if you can find that application? And then these questions kind of apply to this part, this second bullet. This is going to be more about like the application of the spectrum. Okay, so first, before you get into the actual project part of this, I want you to read. I have like a page of reading, and that page has a highlighted section, which is probably the most important part. And then after that, you'll see a table. Okay, so let me go back to the document. So, or the bit.ly address, so you can see what you're doing first, and then I'll give you as a group. stop where you are. You'll have a moment to go back to that as needed. So what I'm expecting is when I give you a group, one, you probably want to sit and talk first about like what you know so far, what your topic is, and then I would make just a Google Slides presentation, and I would have like maybe 1 or 2 slides on this first question, one, maybe 2 slides if you have a lot of information on the second question, and 1 or 2 slides on the third. So no more than like 5 slides, probably 6 slides max. But that will give you an opportunity to utilize some of the images that are provided to you in this link. Because I thought, where'd it go? This one. This is the entire packet, but I've hyperlinked I think the shorter versions up here. Or no, that's just the intro. My bad, that's just the intro. But there are some really good resources. So like if you're UV, if you're UV, for example, there's some really good resources here. You just have to download it. But this is like a printed copy I already have provided for you, but this is the color version. You can even snip examples out of here as long as you can explain what you're talking about. You're good, okay? So as you guys get into groups, I would come up with a Google presentation, okay? So I'm just going to number you guys off, and you guys will do these 4 bullets, okay? Ready? 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Yay! I think you were 4. 1, 2, 3, 4. Yeah. So maybe 1s can come up this region, 2s can go back there at CJ's region, 3s can go in the back corner someplace, 4s can come over here someplace. Let's just start there. If you guys want lab stations, of course, they're kind of being used in similar form, but use lab stations if you need to. There should be 6 people per group. 6 people per group. Oh, some people can grab a paper copy in case it's a little easier. Mass spec people. Mass spec. Through boards. The lab activities. Right there, you guys back there. UV Viz and infrared. You guys can pull desks or chairs if you want. There are some good lab activities. I can show you that.
Oh, you got
Once you divide and conquer, you will need to go back through each other's slides so you can make sure you know what you're talking about.
Chat is back on the too.
Yeah, well, I'll get off the fan. That's good. Here. Well, somebody needs it. I feel like somebody needs it. All right, if you guys would halfway shut your computer so you guys can give them your undivided attention, that'd be great. I'm gonna put a timer on for like 5 minutes, and if you guys need more time, absolutely have it. I just figured this would give us a chance to maybe see them all today. We're gonna see. All right, so if you guys can halfway shut your computer, and if you take pictures, throw them in your papers, like in your notes, because there's not gonna be like, hopefully, maybe more than like 5 little points for a group. That would be relevant. So like for your basic knowledge. All right, I'm gonna just do whatever in 5 minutes.
So we did UV visible spectroscopy, which is the process of using either visible light or UV light to penetrate a solution, which excites electrons, which you can't really see because it's like absorbing the energy, but when it moves back down to the ground state, it releases a visible light, which you can see, and that aids in the identification of the substance.
Electron excitation. Keywords.
So, kind of conceptually give you an idea of how this works or how if you need to change. There's a compound called beta carotene, which is this really long compound with lots of these double bonds you can see here. When it's absorbing light, it emits a very strong color, whereas other compounds such as beta 1 or 3, I don't know, it will emit, when you shine the light of the same wavelength on it, it will emit colorless light, and this is just because this is it's just longer, so the light can pass through all the double bonds, and somewhere along it'll lose steam, and light will be emitted. So this kind of just goes to show that it's not necessarily the wavelength of light that you're shining, it's how the compound structurally is that will change the light.
So they talk about atomic, like on the atom level, electron excitation, and then falling back down, she talked about emitting at a certain wavelength of light. And then on a molecular level, that's called a what system? A double conjugated system. How it can absorb a lot of light, but then also emit a certain color. What does beta carotene emit? It's orange, right? It's in a lot of like carrots. A lot of times in carrots, which make babies orange, they eat carrots.
So spectroscopy of UV lights can be used in chemistry for determining different analytes when you pass it through the substance, the solution, and you can also determine the concentration of different substances based on how much light passes through. So whenever you like shine the light, then you can measure it through the cuvette, and then like the detector here will tell you how much of like the yellow light is passing through.
And like Margaret said, you can also determine how much energy is released as the electron goes from the excited to ground state and which color is produced.
So just two of the things we use for our research
Miss Emma,
Yes.
when the bell rings, you send William Bell to the attendance office for dismissal.
Thank you.
Thank you.
So you can use it for research in pharmaceutical or drug detection. The main thing in the research is determining the concentration of chromophore, which is what gives off the color of a compound. And as she was saying, it all goes back to the color, and then we can tell whether it's an excited state or not excited. And then you can also analyze the speed of reactions. And then in the drug detection, that can be used to identify what types of drugs or like compounds are in specific pills or in a crime scene.
And also you can use it in environment and the quality control of like dyes, inks, and paints. And in the environment, you can test a solution, and you can run it through the spectroscopy machine. And if you can detect impurities, because of like how benzene is a popular impurity in cyclohexane, the nanometer is like 230 nanometers, so it'll like spike, and you can see.
Very good. Okay. Good. All right, so I'd like to use the word chromophore. Chromophore, you guys know what chrome means? Chrome. non-chromium. What's chrome mean? Like color, right? A chromophore is just a little molecule on the end of another molecule that gives it color. And their applications were kind of out there in the real world, which is good. But my next group, lab group number 2, and they're going to elaborate on the applications, because their applications in our world, our AP Chem world, are all labs based on UV vis. There's a clicker.
No one wants to go over here? I got it. Hold on. Maybe the place like this? Put a spot here. Sure. So we're doing laser spectroscopy. I'm just gonna butcher that word. So it's basically we're just taking the concept of any spectroscopy and use it for any like real life purposes. And then like it's not only UV or visible light, it's also an aspect.
And for the labs that involve these, in order to determine about the structure and the substance for the EMS, like electromagnetic spectrum spectroscopy labs, you just give it some energy and see what it does kind of thing. You observe the effect of the substance. So for example, with the beta carotene, you saw the conjugated bonds because of the certain energy of light that you added to it. And then for the mass spectroscopy labs, you separated substance, or you kind of like classified them or like found out more about them just based on mass and charge when you put them through a mass spectrometer. So those are 2 different types of labs that you can create to determine the substance or the body.
So why do we need it? We need it to determine different data points to use in labs, typically involving Beer's law, so the concentration and absorbance between light. Yeah.
Can somebody write Beer's law on the board for me? The whiteboard. Not the orange, JC, not the orange.
Oh, very specific.
That's better. The darker color. Big A equals, and we're going to define these guys.
Absorbance.
Absorbance. Does absorbance have a unit? No, it's just absorbance. Okay.
This is a constant.
Also known as, say again?
Molar absorbency constant.
Right, okay, so molar absorbency constant, that constant is only applicable to a certain solution. So like copper sulfate has its own little a.
Yes.
Lead to iodide has its own little a. Every single colored substance has its own molar absorbency constant.
This is to keep that length, like the width that the light has to go through, and then that's concentration.
Do we get to change that?
No.
We try not to, right?
You should try to change to keep that.
Right.
Yeah.
C.
C is concentration.
And what concentration unit?
Molarity.
Molarity, because that's why A is called the
Molar.
molar absorption.
And it should be linear.
Yes, your data point should be a linear, direct relationship, as Drew said, between concentration and absorbance. Keep going.
Okay, so like we know like all the labs we've ever used, and like we use it a lot for a bunch of different things. Like so modern applications that like are in real life are like enzymes. You can't really tell like or study them directly, but you can study their activity during reactions. So like we have that one lab when we did a reaction, and then we like followed it through the spectroscopy to see like as it became more clear, its transmittance went up or whatever, right?
What was the substance we used that was purple?
Crystal violet.
Crystal
violet. Yeah, CB. So like you can study like reaction rates, stuff like that. You can also do like purity of a substance. Like you know what the graph will look like with a pure substance, then you can keep testing like quality of your new product to see if it matches, to see if it's like impure or pure. It's basically just things that like you can tell what is inside it, like how just compare the graphs and stuff.
So kind of continuing with that, like modern applications, the previous group pretty much hit almost everything we have here, but I'll mention again. So Beer's law, like Drew mentioned earlier, it's relating the absorbance and concentration of light, identifying compounds. So in this case, we use IR spectroscopy, and it's used by chemists so that they can identify unknown substances by getting the absorption of the IR radiation by the chemical bonds. And then also, like Gabby mentioned, with dye, paint, and ink, they use the UV spectroscopy, or it's used in quality control for the development and production of like inks and paints, and this is like pretty much the same thing. They get their substances based on the absorption, everything based on the absorption.
Where would they use that in every day?
Dye, paint, and ink.
But like where?
Markers.
And?
Pens.
House painting.
So like at Lowe's, when they make, you've never seen them? Thank you.
Yeah.
They can use the spectras, especially if they're not happy. And if people know how to use it, like they have the skill set to utilize it. But yeah, they definitely can use it for mixing paints to get the correct, quality control, the correct color that they're looking for. Thanks. One more slide.
Okay, so basically in the pharmaceutical industry, it's used for dissolution testing of tablets, basically obviously medication, pills and things. And then in crime scenes, it's used to analyze blood plasma. And then the only information I found about that was about how the UV spectrum contains information about the absorbance, which tells you about the particle size of the plasma, which is made of proteins that are apparently really complicated because I don't understand anything it said. But that also gives you information about the things that they may have consumed and reasons why the person may have died. And in environmental studies, in freshwater testing of organic material and metals.
And for the pharmaceutical thing, at the pharmaceutical companies, they actually take they'll take some unknown powder and they don't know what it is, and so they'll put it through the mass spectrometer and they'll like divide it into what it is to figure out what it is, or like fentanyl and stuff like that. Just as
And our mass specters gonna love it. IR. Good job, guys. I have you guys go last because you actually introduced a lot. You guys introduced a lot of things. All right, you guys are gonna get moving on this one. You just wait. You just wait. Right.
Okay, so infrared spectroscopy, as you know, infrared radiation is just below visible light. And basically when you expose molecules to this type, it causes vibration of the bonds between atoms. And they always, obviously molecules always vibrate when they're above absolute zero, and they absorb the infrared radiation at a rate corresponding to the rate of their vibration. And if you add more radiation, it'll increase the amount of vibration.
Okay, yeah, and by measuring like the frequency of vibrations, if you have like little vibration, then it means you have a stronger bond. If you have more vibration, it means that it's a weaker bond.
So you have 6 types of vibrations, so everyone up. So the first one you have a symmetric stretch, and it's when you're going out, and it's just stretching out. So you have asymmetric stretch, so you're really stretching out with your right hand, that left hand's just coming in. Yeah, asymmetric. Then you have bends. So with bend, you're gonna go down into a squat as your arms come up. Alright, with vibration, the y-axis, you're just really going, like, arm up, circles, I adore, and then your vibration, the y-axis, you'll put those arms up, and you're just gonna bring it up. Okay? And the vibration of the z-axis, where you're just gonna be like, open your mouth. Yeah.
Guys, this is for fun. Okay, I'm gonna stop vibrating.
Okay, so whenever you send infrared light through any substance, it shows how the bonds vibrate, kind of how Carrington elaborated, and then it displays all of the functional groups. And it's mostly used, like, out of all of these, it's most important for detecting the impurities, and you can identify any substance with it.
So looking at this picture,
there's the different things you can tell. So atoms with less mass move. So it's like a really small person, they're easier to push than a big person like Drew. So so that's why they would vibrate more, and that's how you could identify them. And then okay.
So like carbon bonded to.
We have carbon and Cl, which was, I think, the one on the right. No, the one on the left. Because, yeah, it would be lighter, yeah. So that would be easier to move and vibrate, and then so it would take less energy. So then, for this one, it takes more energy to stretch it, apparently. And then it would take less energy to bend it, because in that one lab, like the ones with the bent shape, I forget.
The molecular modeling lab?
Yes, it was something about, I forget. I'm not with it today. And then single bonds, well, we know that triple bonds are stronger, so they would take more energy to bend. And then from this, we can tell the different functional groups, kind of like how we could tell the difference between the chlorine, and then we can tell the difference between bond types, and then this one's just telling you about it takes more energy to stretch it than to bend. And then this is ethanol, so from the graph you can tell different parts. So red part correlates with this one, and from the way I interpret it, the bigger dip is the more amount of vibration. So because it's a larger, so the small one would wiggle more, and that's why it dips a lot. So this would be a larger to like another larger one. So it's a less of a, that one's all the way down there, but overall it's kind of a little bit less. And then this is an even bigger one. I'm not sure like if it represents triple bonds, but those would dip less than a single bond, which would go lower.
And in college, you have to learn how to interpret these. So you learn like the different frequencies associated, or these different dips differentiated by the atoms, and they give you an unknown sample in a lab, and they're like, here. And you have to run all the tests you can to figure out what it is. It's exciting. And you have to pass the lab.
So in real life, one way that we use IRs, we police use them in breathalyzers because it can measure the rate of absorption and like your breath with like alcohol and such, so you dry.
So another application is you can test like like varnish and paints on dated items, and it's interesting because you can see if a masterpiece is actually fake. And then you can test impurities in raw materials, so it helps to make like pure substances and like more efficient construction.
Hi guys. Oh, you're just about to do it twice. That was an extra slide. Alright, so my mass spec group, let's maybe do this during intervention, just so I don't want to rush you through the last 5 minutes. Thank you. So, here's what I'm looking for. Ready? One, who's already put their solutions multiple choice Scantron in the box? Alright, so I'd like to scan this and get this back to you tomorrow so you can look them over during my review day. 2, I still need to see FRQs, so I've seen some people's, but not all of them. We can check FRQs either tomorrow or during intervention. 3, acid-base equilibria test. We made it through most of the FRQs, but not all of them. Who's done correcting that? We've seen where we are. 1 person. Alright, so if I give you time during intervention to finish that correction set, acid-base equilibria, Unit 8. We went over it last Monday. Yes. I'm going to give you 20 minutes during intervention to finish that up. Okay, so I'm going to ask for you to go ahead and start wherever you need to. If it's finishing up Scantron, if it's finishing up acid-base equilibria, do what you got to do. Laptop's up, okay?